Welcome all to today's ASRG World webinar. We have the 13th of May 2021 and we are streaming from Stuttgart in Germany. Thank you for being with us. My name is Sven Schran and I'm coordinating with ASRG the European locations. The Automotive Security Research Group is now nearly 4 years old and we are a non-profit organization which provides a platform for the automotive security industry as well as related academics or organizations to share knowledge, build powerful networks, and valuable collaborations. This community is for you and it's based on volunteer support. If you want to know more details about ASRG, please check out our webpage at www.asrg.io. Send us your questions via email to hello@asrg.io or follow the links in the description below this video. Maybe you have an idea for a nice project and look for partners to realize it. You would like to start your own location. You have an idea about a service ASRG could provide to the community, or you know a great organization which could partner with ASRG. We are open to hear each idea you have in mind and would like to discuss how ASRG can support. Don't hesitate and get in touch with us. So, this is enough from my side today, and I don't want to keep you tortured anymore because I'm sure you are waiting very curious for our main presentation. Like every time, in case you have questions during the presentation, please write it in the chat window. After this session, we will have some more minutes for questions and answers. And now it's my pleasure to welcome Alfie Eskandari, who will talk to us about establishing chain of trust on an embedded Linux platform. And now I would like to hand over to Alfie. The virtual stage is yours.
Hi, good evening, everybody, and thanks for joining the webinar, and thanks to Automotive Security Research Group for organizing this event. My name is Alfie Eskandari, and today I'm going to talk about establishing chain of trust on an embedded Linux platform. Here is our agenda. First, we are going to see what are the threats to the boot process and how those threats can be mitigated and what are the countermeasures. Then we are going to have some definitions about security and trust, including the root of trust, chain of trust, and the hardware-software components involved. We are going to see the processor security architecture, the i.MX 6 from NXP, and some of its key components from the security subsystem, like high assurance boot and the cryptographic acceleration and assurance module. We are going to see some security vulnerabilities related to the i.MX application processors and also the U-boot bootloader. Then we are going to move on with the code signing concept and architecture. We are going to see what is the code signing, what are the code signing, who are the code signing participants, and what is the NXP reference code signing tool, the code signing tool architecture, and the public key infrastructure tree. We're going to see the image signing and encryption processes. The sign and encrypted U-boot and fit image formats will be discussed, and the command sequence file. And then we see the image authentication and decryption processes, and the details of the image authentication and decryptions will be discussed, and we are going to see how exactly these processes work. And finally, we are going to see a reference implementation of chain of trust and a demo, a chain of authenticated boots, including the U-boot and fit image, which itself embeds the Linux kernel, the device tree blob, and the Rootfs on ramdisk. Then this authenticated boot is going to be extended to support the encrypted boot and also the storage encryption. Boot process is one of the most important aspects of device security. There are so many important stuff is done during the boot, like initialization of the components and peripherals, execution of the bootloader, loading and start of the Linux kernel image, and the execution of various startup scripts and daemons. What are the threats to the boot process? Well, this could be altering the boot process and having control over the critical components, such as bootloader, Linux kernel, and root file system. Someone can run unauthorized and malicious software on the device. And last but not least, reverse engineering of the boot components. We are going to see some examples during our demos about some of these threats and some of these modifications and the countermeasures. And the countermeasures, of course, one option could be having a chain of authenticated boot, which ensures the integrity and authenticity of the components involved in the boot process. And when higher level of assurance is required, we can have a chain of encrypted boot, which ensures the confidentiality of the firmware, making the reverse engineering, of course, not possible, but not impossible, but much more difficult. Here we see an overview of the chain of trust. It starts with root of trust, the foundation upon which the chain of trust is established. This should be really trusted, and if it's compromised, the whole system is insecure. In a chain of trust, starting with the root of trust, each component must first authenticate the next component before transferring the execution control to it. The signature verification is done through the public key cryptography, and the components are signed using the private key, and the verification is done using the corresponding public key certificate. The components involved in a chain of trust, on the hardware side, we can name CPU silicon, memory, peripherals, and on the software side, the bootloader, operating system, and the application software. One important point that I just wanted to mention here, the closer we get to the root of trust in a chain of trust, the more dangerous would be the attack. This means that if someone can have the control of the bootloader, they are able to load their own Linux kernel and consequently to mount their own root file system and the application software on top. So it's really important in a chain of trust, we keep the components, specifically those close to the root of trust, really, really secure. Here we see an overview of the i.MX 6 security subsystem. It includes high assurance boot, which is a library embedded in on-chip RAM, and it executes in trust zone secure world. It runs every time chip is reset, and it's responsible for authenticated boot and encrypted boot processes. The cryptographic acceleration and assurance module, which implements several ciphers and hashing algorithms like AES, triple DES, DES, and SHA. And there is also a dedicated secure RAM used to store the data encryption key during blob encapsulation and decapsulation. It also has a random number generator and a secure key module, which is responsible for managing special purpose cryptographic keys used in key protection mechanism like black keys and the cryptographic blobs. We are going to see the details about this security mechanism in the next slides. The on-chip one-time programmable fuse, which is used to store the superroot key called SRK hash values, and also the one-time programmable master secret key, which is unique per IC. It's also possible to have the revocation mechanism, and there are revocation masks in the OTP fuses which can be burned. And also the security configuration, which tells the device if it's in a closed security mode or it's an open mode. We're going to see the examples also in the demos regarding this. And the last part is the secure non-volatile storage block, which is a logic responsible for monitoring and controlling the chip security states. It determines if the chip is in a trustworthy state or not and controls the CAN. The high assurance boot version 4.1, which is implemented in our i.MX 6 dual-core processor that we have used in this project, offers a good set of features regarding the security. It supports the image authentication, and it also has the superroot key, which is the root public key, and multiple of those, up to 4, is supported, and they can be revoked by writing to the OTP fuses. And the hash value of this superroot keys are bent to the OTP fuses in order to establish the root of trust at the hardware during the boot. The public key cryptographic used is the RSA 1024 to 496-bit is supported, which follows the PKCS1 standard. The certificate format is X509 version 3, and the signature format follows the cryptographic message syntax, CMS, which follows the PKCS7 standard. The key format, the private key information syntax standard, and it follows the PKCS8 standard. So the hash algorithm used is SHA-256. The image encryption is supported, and the image encryption algorithm is AES-CCM counter with CBC-MAC, which provides the authenticated encryption mechanism. The secret key, the data encryption key, can be an AES key from 128 to 256 bit. And there is also a mechanism to wrap this data encryption key, which is called the CAM blob, and the secret key is stored always in CAM secure RAM partition. The protocol used for DEC blob encryption algorithm is AES-CCM, which also provides both the integrity and confidentiality through the authenticated encryption mechanism. The key encryption key can be OTP-MK, which is one-time programmable master key, a 256-bit, unique per IC, and usually it's a factory brand. There are also some other type of the keys like ZMK, and CMK. ZMK is a zeroizable master key, and CMK, which is an logical XOR of the OTP-MK and ZMK. We haven't used this in the project, but the detailed information is already available in the security reference manual of the i.MX 6. But here in this project, we have used the OTP-MK for cryptographic blob encapsulation and decapsulation. We are going to see the details, of course, in the next slides. Before moving on to the code signing and the concept and architecture, I would like to take a look at some vulnerabilities related to the high assurance boot. In 2017, NXP disclosed two vulnerabilities related to the i.MX application processors. One was related to the serial downloader. The serial downloader is a protocol STP called STP, which is used in the hardware commissioning and bring up to store on a device the bootloader and the kernel and the Linux kernel when the device doesn't have any software. In the context of this vulnerability, it was possible to use the STP and download a small section of the code to an unprotected region of the memory. And this, as a result, could allow an unauthorized image to run on the device. Interestingly, this problem was also present in a device which is already configured in the security-enabled mode. The problem was in the boot ROM, and there were no software workaround for it. But possible mitigation could be preventing physical access to the respective STP ports. There are also some variants of the i.MX application processors, which gives the possibility to burn an OTP fuse and consequently disable the STP port on the device, but this is not the case that all the variants have this possibility. The next vulnerability was related to authenticating a certificate. And apparently it was possible to bypass the signature verification by using a specially crafted certificate. And consequently, an attacker could execute an unsigned and unauthorized image on the target. This vulnerability was also present in the boot ROM, and there were no software workaround for it. And the possible mitigation was in order to prevent the remote exploitation, there could be a possibility if someone uses the over-the-air update on top, can implement the validity and conformity check at that stage, but nothing more than that. But both vulnerabilities got fixed by a boot ROM update in new silicon revisions of the affected devices. To be specific, related to our project i.MX 6 dual core or quad core, all the versions below 1.6, the CPU silicon versions below this version were affected, and after the boot ROM update, after this version, the problem got solved. One interesting point that I just wanted to mention here regarding the second vulnerability is that in the high assurance boot version 4, NXP uses the X509 certificate, the standard certificate format. But in their new generation, which is called Advanced High Assurance Boot, they have migrated to a proprietary certificate. And this could be an interesting point that they have used this in order to mitigate any possible, let's say, misuse of the standard certificate in order to be modified and then bypass the, let's say, authenticating a certificate. So they have used the proprietary version of the certificates in advanced high assurance boot. Here we see some vulnerabilities related to the bootloader. The interesting point here is the trend of the vulnerabilities over the time. We see that the number of vulnerabilities in 2019 in U-boot is 20 compared to the just 3 in 2018. So this is actually a really could be a really big concern for us. As we mentioned earlier, the U-boot is the second component after the boot ROM in a chain of trust, and if the U-boot can be compromised, no matter how strong is the security mechanism afterwards, it can be easily bypassed. Here I just tried to list 2 vulnerabilities related to the boot process. The first one is related to the environment variable encryption feature of the U-boot. U-boot provided, I suppose, from the version 2013 or 14 through configuring environment variable and the AES CBC encryption of the environment variables. But apparently they have used the zero initialization vector in the AES CBC encryption scheme, and this could allow an attacker to decrypt the data. As a result of these vulnerabilities, this feature is completely deprecated. The vulnerability was reported in 2017, and in all versions after that, I suppose from 2017-09, the U-boot has already deprecated this feature, so there is no possibility to encrypt the environment variable through the U-boot. The second vulnerability is related to the verified boot signature validation that can result in bypassing the verified boot process. This can be also done through the specially crafted fit image, because U-boot, we have this fit image concept, which is a container and can include multiple binaries like Linux kernel, the flattened device tree blob, and the root fs, let's say init ram fs, and there is possibility for signature verification of all these components, which is already embedded in this fit image. But in the context of this vulnerability, this could be also vulnerable. So we couldn't rely on this. But this, I suppose, must have been fixed in the newer versions of the U-boots. Here we see a short introduction about the cryptography in terms of symmetric and asymmetric approach. In a symmetric approach, the same key is used for encryption and decryption, and they are usually efficient and normally faster than the asymmetric approach. The secret key is shared and must be protected in this approach, and that's actually the problem. In the asymmetric approach, the public-private key pair is used, and the private key for encryption and the public key for decryption. They are usually computationally intensive and normally slower than the asymmetric approach. But the problem, there is no concern regarding the private key since the public key is shared. Let's move on with the code signing concept and architecture. Here we see an overview of the code signing participants, which includes the certificate authority responsible for protecting the top-level CA key and for certifying lower-level code signing keys. It provides the code signing certificates to the signature authority. And the signature authority is responsible for performing the act of code signing and providing the code signature. And the manufacturer is responsible for requesting the digital signatures across the product software. The code signing tool provided by the NXP is a set of command line tools running on a host computer. It serves as both certificate authority, CA, and the signature authority, SA. It allows a manufacturer to control all aspects of the signing process. It establishes a PKI tree of keys and certificates, which is the CA function needed for the code signing. It also generates digital signatures across data provided by a user, which is the SA function. Signatures generated by CSD are included as part of the end product software image. Signatures will be verified by the hub at boot time. In case of encryption support, CSD generates a one-time AES data encryption key, which is used to encrypt the image. The CSD can take two main inputs, the binary image or images to be signed and the command sequence file. The command sequence files are description files, which are used at the time of signing by the code signing tool, and they determine which keys and certificates to be used and which areas of the image to be signed and or encrypted. And during the runtime and boot time, tells the hub which keys and certificates to be authenticated and installed, and which areas of the image to be authenticated and decrypted. Here we see the code signing tool architecture. It consists of two main parts, the front end and the reference backend. The front end contains all the NXP proprietary operations of the CSD. The user interface part providing the code signing and encryption output, such as signature binary, encrypted image, and data encryption key. And the reference backend contains open source cryptographic libraries, and it uses the OpenSSL command line and libraries for generating code signing and encryption keys and certificates and signatures. CSD acts both as CA through the use of OpenSSL commands and as signature authority through the use of the OpenSSL library. So as we can see here in the reference backend provided, there are a set of OpenSSL commands used for generating the key and pair, the RSA key pair, generating the certificate signing request, generating the certificate, and converting the certificate to X509 format. And as a result, we're going to have the code signing certificates here. The code signing certificates are applied to this arcade tool, which provides us this arcade table containing the public keys and this arcade table hash containing the hash value of the public key certificates. The code signing certificates are also mentioned in the command sequence file, which tells to the CSD which areas of the image to be signed and encrypted. The code signing keys are also applied and used by the OpenSSL library for the RSS signing and for the used by the AES library for the AES CCM encryption purposes. And there is an adaptation layer which plays a role of wrapper between the OpenSSL libraries and the CST front end. And as a result, after we are going to have the signed and encrypted image as an output, and the hub data, which in case of signing includes the command sequence files, this arcade table, the certificates, and the signatures, and in case of encryption, the standard output of the AES CCM, which is the nonce, the number used just once, and the message authentication code. There is also data encryption key is created, which is used to encrypt the image with it, and then we are going to see in the next slide how we are going to protect this and append it to our image to be used for the decryption process. The data encryption key itself can also be protected on the host machine or in an environment that there is a need for protection when the key is transported between, let's say, two different departments from R&D to production or stuff like this. And there is also the possibility to do this. The code signing tool provided by NXP is flexible in a sense that it gives the possibility to replace the reference backend. The backend replacement is done when higher level of security is required. So the reference backend can be replaced with a different solution, such as hardware security module using the PKCS11 interface. This offloads the cryptographic operation to HSM. OpenSSL, which actually this feature is provided through the OpenSSL engine API, which makes it possible to use alternative implementations for some of the cryptographic operations. As we can see here, so this is not just restricted to the hardware security module. Any kind of emulated HSM on the software side can also get interface through the PKCS11, the cryptographic token interface standard. For example, Soft HSM2 or Utimaco HSM simulator or any other brand which follows the same. PKCS11 standard. And then this can go through the OpenSSL engine API and the adaptation layer and get connected to the front end part of the code signing tool. The required work is, of course, to replace the OpenSSL commands, OpenSSL library, and AES library, and new adaptation layer software needs to be deployed to provide the equivalent functionality to the front end as the reference backend. Here we see an overview of the public key infrastructure tree. PKI is a hierarchy of keys and certificates in which each certificate, except the root certificate, can be verified using the certificate above it. This ensures the authenticity of the public keys. It includes the CA key, the topmost key, and it's only used for signing the SRK certificates. The SRK, the super root key, which are up to 4, is supported, and the hash value of the SRK certificates are burned to the OTP fuses to establish the root of trust at boot time. And the first 3, SRK 1, 2, 3, can be revoked. The SRK also includes 2 subordinate key, the CSF key, which is used to sign and authenticate the command sequence file, and the image key, which is used to sign and authenticate the software image. Here in the next slide, I've just tried to provide some more details about the public key infrastructure. All the private keys generated as part of the PKI establishment are protected, and they are protected and they are encrypted with triple disk block cipher and a password which is provided using the keypass.txt during the process. And this follows the PKCS number 5 password-based encryption standard. But this can also be changed and modified to any other requirement. Each certificate, as we mentioned earlier in a PKI, signed by the private key of its upper level, this provides a mechanism to verify the authenticity of the public key. So as we can see, each element is a combination of a key, which is the private key, and certificate, which is a signed public key. In case of CA, this is a self-signed certificate. And for the SRKs, all the SRKs from 1 to 4 are already signed with the CA private key. And one level down, the CSF and the image also image public keys are also signed using the SRK private key. Here we see the real implementation and that we have used in this project. On the right side, we have the keys, and on the left side, we have the certificates. As we can see here, the CA private key has been used to sign the SRK public keys, and as a result, the certificates are generated, and this process certifies the SRK key. And similarly, one level down, the SRK private keys has been used to sign the CSF and the image public keys, and as a result, the CSF and the image certificates are generated. And at the end, the CSF and image private keys are used for signing the command sequence file and the image, and also authenticating these parts during the boot. indicates the CSF contents from which is executed. Similarly, the hash value of the CSF commands are calculated, and this hash will be signed using the command sequence file private key. And as a result, we are going to have the CSF signature here. And during the runtime, the CSF signature appended to the image will be authenticated using the CSF public key that we have already authenticated in this process above. And then as a result, we are going to make sure that the command sequence file, which are already appended to the image, are not modified, and this actually ensures the integrity of the command sequence file. Here we have the last two commands related to the signing: the install key command, which authenticates and installs the public key used in authenticating data. Used in authenticate data command down there. So similarly, the hash value of the image public key is calculated. This hash is signed using this RK private key, and the image certificate is generated. And the image certificate will be authenticated during the runtime using this RK public key. The authenticate data command verifies the integrity and authenticity of the image data in memory. So the hash value of the image data will be calculated during the signing process, and this hash will be signed using the image private key. And the image signature, as a result, is created. And during the runtime, the image signature will be authenticated using the image public key that we have already authenticated in the above diagram. And as a result of this comparison, we can make sure that our image data hasn't been changed, and the integrity of that is already ensured. Here we see a real example of the U-boot command sequence file. One thing that I just wanted to mention here, I haven't provided the fit image, but the fit image also follows the same concept. Here we have the header that we haven't discussed so far. It just has some information about the version of the hub 4.5, the security configuration if the device is open or closed, the hash algorithm that is used, the certificate format and the signature format, and the engine, which is the cryptographic acceleration and assurance module. As we can see here, the first command, install SRK, has two parameters: the file parameter, which points to the SRK table, and the source index, which is an index of the key location in the SRK table to be installed. This is going to be installed in slot 0 of the hub internal public key store. So we have the install CSF command afterwards, which points to the CSF certificate and is used to authenticate the CSF data. And the key which is used to authenticate the CSF data will be installed in slot 1 of hub internal public key store. The next command is authenticate CSF, and the authenticate CSF does the authentication of the command sequence file contents itself using the key that we have already authenticated in the previous step. The install key has the parameter verification index, which is a key slot index used to authenticate the key to be installed. This means the install key command will authenticate. Yeah, exactly. So this authenticate the key, the image key, which is already installed in slot 0. That's why we have the verification index 0 here, and also has a target index, which is a key slot in hub public key store where key will be installed. This is the slot 2, and also it points, has a parameter file which points to the image certificate. And finally, we have the authenticate data, which has a verification index parameter. This is the key slot index used to authenticate the image itself. Since we have authenticated and installed the image key used for authenticating the data itself in slot 2 here as a target index, then the verification index will point to the slot 2 that we have already authenticated here. And of course, at the end, we have the block command, which has multiple parameters, including the load address of the image in the memory, the offset in the flash, the size of the U-boot in bytes, and the image name. Here we see the image encryption procedure. Similarly, it starts with generating the keys and certificate, generating this arcade table and if use hash, and then programming this arcade table hash value to if uses. Then we are ready to sign and encrypt the image using the CSD tool, providing the command sequence file. And as a result, the signatures are generated, the image is encrypted, and the secret key, data encryption key, is also generated. The next step would be generating the data encryption blob, which should be generated in a securely booted U-boot. So in order to be able to have the data encryption key, which is our secret key, and is used to encrypt the image, to store it and append it to the image without any fear, we have to create a cryptographic blob, which is called DEC blob. And this must be done in a already securely booted U-boot, because only in this case, the OTP key, this master key that we were talking about, is available to the CAM. Otherwise, there is just one test key, which is a template, is available to the CAM, and CAM will use this one for creating the DEC blob. So this blob mechanism just gives us the possibility to store securely the data encryption and the wrapped version of that, which is the encrypted version of that, on the image. And then after creating the DEC blob, at the end we have to append the HAB data to the image. In case of signing, all this data should be included, and in case of encryption, the nonce and the MAC, and also the DEC blob in this case. So the DEC, the data encryption keys, and one is a one-time AES 128-bit key and is used to encrypt the image. The DEC blob must be generated during the manufacturing on each processor that has used the same data encryption key for encryption and then attached to image on the device. The DEC is common to all ICs using the same encrypted image, but the DEC blob is unique per IC. We're going to see in the next slide how is the process, and then we understand that why the DEC blob is device specific. And this is really important because then an image which is encrypted on device is not, there's no possibility to decrypt it on a different device, because the DEC blob will be different. Here we see the image format on the flash related to sign and encrypted U-boot and fit image format. Sorry. On the left side, we see the U-boot. Similarly, we have the boot data structure, and one point here in the signed and encrypted version of the U-boot, we have the boot data structure. They don't contain any confidential data and are used by the ROM before the CSF is processed. So therefore, these data structure remain in plain text and are included in the digital signature, so they are not encrypted here. So we have the boot data structure, including the IVT, the boot data, and the DCD, that they are signed and the signature are appended, and the U-boot itself, which we call here the payload of the image, and this is called the header of the image. And this is actually encrypted, and the nonce and the MAC is also appended to the image. This is going to be padded, and the data encryption blob will be appended to the image. Similarly, for the fit image case, we have the fit image header and the fit image itself, which is considered for us here the payload, and they're going to be encrypted, and the nonce and message authentication code will be appended. And the IVT here is considered as the header, the image vector table, and this is just going to be signed, and the signature information and all the other fields will be added. This is going to be also padded, and the DEC blob is also appended at the end. Of course, the fit image, we have already mentioned this, the fit image should also be padded to the next 4K boundary due to the page size. So this is also important in this process. And similarly, in both cases, the size of the HAB data is a maximum of 2000 hex, which is 8K. Here we see the process related to the encrypted boot. We have two more commands in this case, the install secret key and the decrypt data command in case of encrypted boot. So as we can see here, the image data will be encrypted using our secret key, which is the data encryption key, and the image will be encrypted. But in order to protect and append this data encryption key to our image to be used during the runtime in the decryption process, we have the DEC blob encapsulation mechanism. And during this process, a random key, which is 256-bit, is generated by the random number generator of the CAM. The data, which is the data encryption key here, is encrypted with this random key following the AES-CCM scheme. And then the random key itself is encrypted using the OTP-MK, which is our key encryption key and unique per device. And as a result, we are going to have the DEC blob here. During the runtime, the first thing is that to extract this data encryption key from this cryptographic blob, the process works like this. The random key is first decrypted using the OTP-MK, and then the data, which is the data encryption key, is decrypted using this random key. As a result, we are going to have the secret key extracted here. And the encrypted image will be decrypted using this secret key, and the process would fail or pass depending on the outcome. So just to wrap up this stuff, the DEC blob, as we mentioned, is a cryptographic data structure and provides both integrity and confidentiality protection of the data encryption key and gives us the possibility to store it on the non-volatile storage. Here we have an example of the U-boot command sequence file in case of encryption. It's quite similar to the one which we used for signing case, but there are some minor differences. The first is this unlock command, which prevents the random number generator feature of the CAM from being locked when exiting the internal bootram stage. This actually differs the random number generation or the random number generator instantiation for post-HAP software. For example, bootloader and Linux kernel. Bootloader case, we already saw how we are using in this process the random number generator for creating the cryptographic blob. And the Linux kernel case, we're going to see when we discuss the storage encryption and generation of the black key blobs. And here, as we can see, there are two differences. The two commands that we already discussed, the install secret key command has multiple parameters, the verification index, which which determines which master key encryption key should be used, the OTP-MK, the ZMK, or CMK. We have used the index 0, which used the OTP-MK, which is unique per IC. The target index is the target key slot in CAM secret key store in secure RAM where key will be installed. This is going to be a slot 0. And the key name, the key length, which is 128-bit, and the absolute memory address where the blob should be loaded into the memory from the flash, which is already appended there. The decrypt data command has also the verification index, which is the key slot index used to decrypt the image. We have already installed and extracted the secret key in slot 0. That's why the verification index for decrypting the data is 0. And the size of MAC in bytes, which is even number between 4 and 16, and here we have used the maximum, which is 16. And the block command, which actually shows the load address of the encrypted U-boot in the memory, the offset in the flash, the size in bytes, and the U-boot name itself. Here we see the image signing and authentication process. During the signing process, the hash value of the image is calculated. This hash will be signed using the private key, and as a result, the signature and the HAB data will be appended to the image. We have seen already how the root of trust is established by comparing the hash value of the public key certificates appended to the image with the hash value of the SRK already burned to the OTP fuses. During the authentication process, the hash value of the image will be calculated, and we're going to have the generated hash here, and the signature appended to the image will be authenticated using the public key, and we are going to have the reference hash. And the outcome of this comparison will determine that if the authentication process was successful or not. Here we see the image signing and encryption, and also authentication and decryption process. On the left side, we have the image signing and encryption process. As we mentioned also earlier, the image is divided to two parts, the image header and the image payload. This image header was this boot data structure that they are just signed. That's why the hash value of it is calculated, and it's signed using the SRK private key. And of course, as a result, the signature information is appended. The image payload, which is the U-boot or the fit image itself in this case, are going to be encrypted using AES-CCM with the data encryption key, which is our secret key. And there's also a mechanism that we also mentioned for encapsulation of the data encryption key and generating the dec blob and appending it to the image. During the runtime, there are two processes done independently. The first is the signature verification of the image header. So the signed header hash value is calculated. This forms the generated hash, and the signature appended to the image will be authenticated using this SRK public key, and we're going to have authentication has passed or failed. And for decryption process, first the blob decapsulation mechanism will be executed, and as a result, the dec blob will be decrypted using OTP-MK, and we are going to have the secret key here. And the encrypted payload, providing the nonce and MAC as initialization vector and tag for AES-CCM decryption, will decrypt the image payload for us, and this is actually the authenticated decryption process, which can fail or pass depending if the image has been modified or not. One thing that I just wanted to mention here, the image payload is authenticated with respect to the data encryption key using AES-CCM. Authentication with respect to the SRK can also be implemented, but this is a different thing, and there are some specific application notes that you're explaining this process as well. Here we have a chain of trust reference implementation, and actually the chain of authenticated boot, which means in this case the U-boot including the kernel fit image. So as we can see here, the fit image is a container containing the Linux kernel, the FTD blob, and the init ramdisk. And through this, let's say, packaging in one just single container, we can actually provide a mechanism for integrity and authenticity check of the fit image. Exactly. So then we are going to move to the next slide, that we have extended the chain of authenticated boot to support the encrypted boot and storage encryption as well. Similarly, here at the boot ROM stage, HAB reads the U-boot command sequence file. It authenticates SRK, CSF, and image certificate, and then authenticates the CSF command. uh, have, uh, does the decapsulation of the dick blob through the CAM engine and authenticates and decrypts
Okay,
the U-boot image. If all the stages are, all authentication and decryption processes are
alles klar.
okay, the boot
Gut,
ROM transfers the
ciao.
execution control to the U-boot. At the U-boot stage, uh, U-boot requests HAB through the HAB API to route the fit image command sequence file. It authenticates the SRK, CSF, and image certificate, and authenticates the CSF command. It decapsulates the dick blob through the CAM engine and authenticates and decrypts fit image. If all authentication and decryption results are okay, U-boot proceeds with loading the Linux kernel, the kernel fit image to the memory, and proceeds with the rest of the boot. The storage encryption here, we have used this encryption at block level, which uses the DM crypt, and DMCrypt itself uses the kernel crypto API. As a result, a new cryptographic, a new encrypted block device is created, and all the writes to this device are encrypted and reads are decrypted. The black key feature of the CAM provided by the CAM driver and CAM keygen user space application is used, and the kernel key management and retention facility called keyring is used for the key provisioning. In the next slide, we are going to see the details how the storage encryption works. So the black key is a mechanism for protecting of user keys against bus snooping while the keys are being written to or read from memory external to the SOC. So how the black key encapsulation and decapsulation works? Well, the CAM encrypts the key as black key before the key is copied from a key register to memory. And then the CAM decrypts the black key from memory into a key register before using it in a user-specified cryptographic operation. The key used to encrypt or decrypt the black key is held in a 256-bit key register, which is not power cycle safe, and at each power run, a new key is generated by the random number generator and placed into the key register. We see through this mechanism and having an intermediate register between the CAM and the memory, they have provided a mechanism that always the private key or the secret key used for the storage encryption will be seen encrypted in the RAM. And the black key offers two encapsulation schemes. AES ECB, which of course is not safe and can leak the information through the known process of the AES ECB, and they can just be used for quick decryption schemes when it's needed. But when higher level of assurance is required, we can use the AES CCM, which actually guarantees both integrity and confidentiality of the secret key used for storage encryption. The CAM driver introduces two cryptographic transformations here in the kernel, and this leads to the use of the black key for this encryption and decryption. And this is already provides the infrastructure for the kernel crypto API. It also introduces a new key type named CAM TK relative to the CAM tagged key, which is this black key for the kernel keyring. So as we can see here, the CAM keygen create command, which is this user space application, has two output, generates the black key itself and the black key blob, which can be stored in the flash. During the encryption process, the generated black key will be added to the kernel keyring using the key control utility. And then DM setup is used to do the storage encryption. During the decryption, first the black key blob will be imported using the CAM keygen, and then this imported key will be added to the kernel keyring as a logon key. I forgot to mention here as well, this is also as a logon key to the kernel keyring, and then DM setup will be used for the storage decryption. The logon key is type of kernel keyring keys. They have the keyring, the user, and the logon key, but the logon keys are provided here to add higher level of assurance since they don't disclose the key payload to the user space. So here we also have an overview of the different components involved in the storage encryption and the infrastructure also provided by the Linux kernel, including the kernel crypto API, the keyring, and the decrypt, and also the stuff provided by the CAM that actually we can realize the storage encryption here. Here, we're done with the presentation part, and we have used the Mars board from Mbestec, which is a tiny board providing an i.MX 6 dual-core ARM Cortex-A9 running at 1 gigahertz, and also L1 cache and L2 cache, and also eMMC 4 gigabyte DDR3 RAM, and also a few amount of SPI flash. It also has some peripherals that we have used here, the SD card slot, and much more which are not relevant to the project. In the first part of the demo, we just want to investigate a system which is not secure. This means the U-boots and the fit image are not signed and encrypted. Let's have a look for the first part to the system that the U-boot is not signed and encrypted. So we stop the auto boot process here, and as we can see here, we already run a version of the U-boot which is not signed and encrypted. We use the have status command in the U-boot to get the security status of the device. And as we can see here, the secure boot is disabled, and we get the multiple instances of the hub events, including the hub event data and some information about why this has failed. The hub event data can be interpreted using the hub API documentation in order to understand the root cause of the problem during the development. But of course, here we have the device that the U-boot is not signed and encrypted. That's why we get these multiple hub events. And yeah, as we can see here, so the status of the hub engine, which is the hub failure, and the reason that this has happened for the first one, it was hub invalid signature, and the context in which this problem has happened, and the engine itself. So here we just take a look at the U-boot which is not signed and encrypted. For the next step, we are going to manipulate this version of the U-boot. So we have used Ghidra from National Security Agency, NSA, which is an open source reverse engineering tool. So we import the U-boot binary as a project to the Ghidra. We select the architecture, which is, in our case, is ARM v7 little endian. This gives us a summary of the binary itself, and then we try to open this project in the Ghidra. We let the Ghidra to do the analysis on the binary, of the U-boot binary. And as we can see here, since the U-boot is not signed and encrypted, we can see the U-boot environment variables and all the defined string included in the image, since they are not encrypted, as a part of defined string on the window at the right side. Now we try to find the boot command, which is part of the U-boot auto boot process, and at the moment it's a valid string which says run boot fit image, and of course the device boots after running the boot fit image script. Now we try to manipulate this boot command, which is part of the environment variable. Yeah, I suppose now we are trying to find We have switched to the byte view, and we have to go to the edit mode, go to exactly to that line and start to edit it. And now it's possible, yes. So we changed the boot command from boot fit image, let's say, to something like hacked. So this is done, and we can also change the boot delay, which is the delay when the U-boot boots as part of the auto-boot process. It actually has a delay in order to press a key and run to the U-boot prompt. This we can also change to something else. Let's say 9 seconds. So we save the project. And then we export the manipulated U-boot binary. So we export it as a binary. So we have patched in this process the U-boot, which was not signed and encrypted. So this is done, and in the next step, we are going to test this on the target. So we reset the board, we stop the auto boot process. We have the environment variable boot command. This is before the updating the suspicious image. That's why it's still run a boot fit image. And then we can also see the boot delay, which is already 2 seconds. So we reset the board. So the Linux image, the Linux kernel is booting. So we run into the Linux shell, and we have scripts to update the manipulated version of the U-boot on the flash. So it's already located on the SD card. We erase the U-boot partition on the SPI flash. The image is read from the SD card, and now we are copying the U-boot image back to the SPI flash. So this is going to take a while. So it's done. So we just do a double check by looking at the contents of the flash to see if everything is okay, looking normal. This is the case, and then we reboot the device. So it's rebooting now, and we already see that the 9 second of the boot delay is already there through this manipulation. And of course, the device, after, as part of the auto boot process, wants to execute the boot command, but the boot command now has changed to the hacked, which is absolutely invalid thing, and it can run the fit image, the run fit image script, which we have already changed. We can actually double check also in this manipulated version the boot command, which is, as we can see here, is hacked in this case, and the boot delay, which is 9 seconds as part of this manipulation. So we saw that when the image is not signed and encrypted, we can easily manipulate the U-boot and interfere with the boot process. This could be much more dangerous thing. We just wanted to have a proof of concept and show and verify the functionality. As part of this process, one can actually develop their own script, load their own fit image. They can do this destructive thing on the device. For the next step, we are going to actually take a look at the not signed and encrypted fit image on the target. So we reset the board, we stop the auto boot process. Here we read the fit image from the from the SD card and load it to the memory. The U-boot also provides the image info command that we can actually take a look at the details of the fit image. As we can see here, we have image 0, which is the kernel. The image 1 is flattened device tree blob, and the image 2 is our RAM disk. So we just verified this, we reset the board. And the normal fit image, which is not signed and encrypted, boots completely. So in the next step, we are going to manipulate this version of the fit image. So we import the fit image to the Ghidra as a project. We select the architecture, ARM v7 Little Endian. And then we open the fit image. We let the Ghidra to do the analysis of the fit image binary. This is going to be a time-consuming part since the fit image is quite big compared to the bootloader. I'm just going to skip that part and jump to the point that we have the information decoded. Yeah, exactly. Similar to the U-boot case, here, since the image is not encrypted, we have, as part of the define string, all this stuff, the most easy thing that we can actually look at it. There is also the possibility to explore the U-boot binary through the function graph feature of the Ghidra. There are so many stuff possible here. As an example, for example, from the entry point of the program, we can just look at the transitions as an example to see to where and under which condition these transitions happen. But this is outside the scope of our presentation. I just wanted to have a snapshot of the feature of the Ghidra and how it can be used, or let's say misused, for hacking process. In our case, we are just going to modify something in the fit image header. This is very simple modification, but destructive enough to break our device. So we are going to make multiple bytes 0 there in the fit image header. Then we save the project. And we can export the modified version as a binary. So for the next step, we are going to try and test this modified version of the fit image on the target. So we power on the board. And as we can see here, the fit image has already been changed. So the fit image is read from the stick card and loaded to the memory, but we have problem in loading kernel from the fit image. Why? We have changed the fit image header, and now we have got the error that the bad fit kernel image format is detected and cannot the kernel image. As a result, from the U-boot stage, we cannot load the fit image, and it's broken. We can double check this using the image info command of the U-boot. Of course, we will have the same result to to see the contents of the fit image, which is already loaded into the memory at that address, and we say that we get the bad fit image format. So we could easily do something destructive on the device and break the device, since the image was not signed and encrypted. In the second part of the demo, we are going to take a look at the system which is secure. Okay, here, for the sake of completeness, I've been trying to be comprehensive enough and test all the possible, modify all the possible sections of the image, including the header, including the payload for both U-boot and the fit image. But the concept is actually the same. If somebody is interested, there's also already a YouTube video for including all this tests, which is done there. But here, in order to keep the time box, I'm just going to focus, let's say, just to look at the signed and encrypted U-boot, and also see one case from the U-boot, and also similarly for fit image, and then the last part, which is the storage encryption. Then let's take a look at the signed and encrypted version of the U-boot on the target. We power on the board, we stop the auto boot process, and as we can see here, we are already running the U-boot, which is the signed version. The secure boot is enabled. We issue the have status command in order to get the security status. The secure boot in this case is enabled, and we don't have any hab events. So this means that the secure boot has been successful, and we have got no hab event, and the deployment were completely successful. Now we try to read, let's say, 256 byte of the U-boot from the SPI flash. And as we can see here, we have the signed version of the U-boot, and we can see part of the U-boot environment variable. For example, this hit any key to stop auto boot. This we see during the runtime. Since the image is signed, so this information are still readable. But the encryption actually would lead that we will have the case that we cannot read it. We are going to see it, but in this case we can read the information. So we have an environment variable called U-boot image, which points to the U-boot image, which we can actually change this environment variable to a different U-boot version. Now we had the signed version. Now we want to actually change it to the signed and encrypted version. Then this U-boot is going to be used for the device. So we double check the U-boot image. Now it's the U-boot signed and encrypted. And then we run another script which updates this U-boot on the SPI flash. So we were running a signed version of the U-boot. Now we have updated the device to have the signed and encrypted version of the U-boot to verify some stuff. So it's done. And then we reset the board. We stop the auto boot process, and from the prompt, we already see that the signed and encrypted version is running, but we are not going to trust this. We run the hab status command, the secure boot is enabled, and there is no hab events found. Let's read the same area of the SPI flash and check the contents in this case. So as we can see here, we read the same area, but now the contents are encrypted, so there is nothing meaningful that can be interpreted by us. Compared to the case that we had just the signed version, and we could read and interpret, let's say, those parts of the U-boot environment variables. So this was a tour of the signed U-boot and signed and encrypted U-boot on the device. Now for the next step, we are going to see one case of manipulating of the signed and encrypted U-boot. If you remember, we had this payload and header concept during our code signing and encryption process. Now we are going to change the payload part. I'm choosing this. And we're going to hack this. So we actually load the signed and encrypted U-boot. We select the architecture. be imported as a project into the Ghidra, and we open it and let the Ghidra to do the analysis. So as we can see here in this case, since the U-boot is encrypted, none of the defined strings in the U-boot can be read and interpreted since they are encrypted. And the U-boot environment variables are also part of those defined string. They are just a string and nothing more than that. But anyway, we can still do some manipulation in the payload part. If you remember from the slides, we had the boot data structure, the first block from address 0 to address C00 in hex. That part was the boot data structure, and the rest was the payload. Now we are going to modify something afterwards, let's say at this address, C50 hex, which already modifies blindly something. It doesn't matter. We just want to verify the functionality. So we make some bytes 0 in an encrypted and sign an encrypted version of the U-boot, and we save the project. Then we have to export this binary. Okay, done. And then we are going to test this on the target. So we power on the board, we stop the auto boot process, we already run the signed and encrypted version of the U-boot. We reset the board. This is the version which is not modified. Now we are going to update the U-boot with the modified version. So the Linux is booting. Okay, we're onto the Linux shell, and as we have seen before, we have scripts to update the manipulated version of the signed and encrypted U-boot. So we mount the SD card, we erase the U-boot partition on the SPI flash, checking if the erase process has been successful. We copy the image of the U-boot, how it should look like. And this is not encrypted and just signed, so everything looks to be okay. Then we reboot the device. So as we can see here, the reboot has already been executed, but the device doesn't boot. Why? Because we had a signed and encrypted version of the U-boot that we have modified, and since this is modified, when the boot ROM does the signature verification and decryption process, let's say authentication and decryption process, this would fail due to this modification, and we are not able to run the U-boot on the device. Boot ROM won't actually boot the U-boot on the device, and it stays in a fail-safe mode. Is in a fail-safe mode, recovery mode, and even if somebody plugs and tries to access or load an image through this fail-safe mechanism, which is this USB recovery mechanism, even in that process, the image should be a valid image, signed and encrypted, so with the right keys, and this won't be possible. So here, for the next part, we're just going to take a look at the signed and encrypted fit image in this case, the normal one running on the device. So we stop the auto boot process. We have an environment variable called kernel image in the U-boot, which points to the fit image to be used for the boot process. And we have the boot command. So we are gonna actually read the fit image from the SD card, load it to the memory, and then look at, to let's say 256 contents of this fit image. And as we can see here, there is nothing that can be decoded. This should be some meaningful text at least there, but this was not the case because the fit image was now the fit image boots. Yeah, because the fit image, sorry, because the fit image was signed and encrypted. That's why we couldn't see the contents there. Now we scroll up a bit in order to understand what has happened. So we read the fit image, which is signed and encrypted. We authenticate this loaded image to the DDR memory. And as a result, we can see, okay, the secure boot is enabled and there is no hub event found. And in this line before the loading from our U-boot script, we see that the kernel fit image authentication and decryption was okay. So it's booted without problem and through the authentication and decryption process. So we do a reboot. We stop the auto boot process. And now we want to change this kernel fit image to the version which is just signed and not encrypted to do some investigation of the image itself. So we change it to the fit image signed. We double check. And we try to load this fit image into the memory, which is just signed. So this is done, and then we try to read 256 byte, let's say something, in order to just see the contents. And as you can see here, the same contents, since in this case fit image is only signed, we can read and interpret this stuff. But in the previous case, that the fit image was signed and encrypted, this was not possible. This is a double check of what has been implemented in terms of signing and encryption there. So now we run the boot command in this case. And we expect the same process. But anyway, we are going to double check. Now look at it. So we just scroll up a bit to see what has happened at the beginning. Yep, here. So we read the fit image in this case, which is signed. The authentication is done. And we have the secure boot enabled and no hub events found. And we still see the kernel fit image authentication and decryption okay from our U-boot script. So the device has booted properly. Now, for the next part, we try to manipulate the signed and encrypted fit image, the payload part. So we load. We select the architecture, import it to the Ghidra. And then we're going to open the Ghidra project. Yep. So similarly, since the fit image is signed and encrypted, nothing can be read and interpreted from the defined string in this case. But anyway, we are going to switch to the byte view. And it took much less time. I didn't need to go forward because there were nothing that can be decoded by the Ghidra. The process was much faster. And we are going to change in the fit image header, which is still part of the payload of the fit image header and itself are part of the payload. The image vector table was the header. So we just makes multiple bytes 0 there. We save it, and then we export it as a binary. Good. This is done, and now we are going to test this modified version of the signed and encrypted field image on the target. So powering on the board, we double check the kernel image environment variable, which is pointing to the field image signed and encrypted. We set it to the field image signed and encrypted, which the payload is hack. This is already on the eMMC, and then we run the boot command, which tries now to load this version of the field image. As we can see here, we read the modified field image. The authentication is done, but the results of the authentication, okay, secure boot is enabled in terms of configuration, but we have got a hub event here, including the event data, and the process of the signature verification and decryption has been failed here with the reason of the hub invalid signature. And at the bottom down there, we have the kernel field image authentication and decryption error. This is part of our U-boot script. At this stage, the device is also getting stuck. So this means that the boot RAM has loaded the U-boot. U-boot was okay. The U-boot has tried to load the field image. This hasn't been okay because we have manipulated the field image. But then at this stage, we have the devices get stuck at the boot RAM USB recovery mode that still needs a valid image prepared, signed, and encrypted in that case in order to recover this device. So this device never boots since the image authentication and decryption process has failed. So we see that it was not possible to modify. Okay, it was possible, but it was not possible to run an unauthorized and malicious and modified version of the field image on the device. For the last part, we are going to take a look at the storage encryption. So if you remember from the slides when we were discussing the storage encryption, we have the CAM keygen user space application, which can create for us two outputs when we execute this regarding the secret key used for the storage encryption. One is the black key itself, and the other one is the black key blob. The black key itself, of course, is used for storage encryption, and it's always seen encrypted on the memory to avoid bus snooping attack or mitigate it. And the black key blob is also a safe mechanism to store the black key blob securely on the device somewhere on the flash itself. So here we are going to actually take a look at the this black key that we have used in this project. One remark here: we have used a black key, which is a random black key with the length of 16 byte, and it's gonna be encrypted using the AES CCM, the more secure approach. And here, this is how the blob looks like. For the next step, we see the imported key that we have used the CAM keygen import command to import our key from this key blob, but of course in an encrypted way on the flash and also on the memory. Now we are going to actually verify this, and we are going to do multiple imports from the same blob on a running system and then compare the result to see if we can see some correlation there or not. So then we are going to actually try another import. And as we can see, it's from the same blob located on the flash. compared to the one up there, but we change the name and we import this one. Then we try to read back the contents. Good. So now we're going to try one more import, and then we want to double check the contents. As we can see here, when we compare these three imported keys, except the key payload, except the key header, which is the same in three cases, the key payload itself is different. Since at each run, this has been imported and has been encrypted using the AES-CCM approach. So one can ask why the size is 48 byte. This has a reason. We said, okay, our key is 16 bytes, but through the AES-CCM encryption, according to the security reference manual, the two more fields will be added as output, which is the message authentication code, which is called here the integrity check value, which is a 6 byte, and the other field, which is I just forgot it. In mind, exactly the nonce, this which is used as an initialization vector during the decryption process for AES-CCM. 6 byte, that one as well. So including those plus the key size and the header information, we are going to have 48 byte. As you can see here, this 30 in hex means 48 byte is the encrypted black key size seen on the flash and also on the memory. Yep. Here in this project, we have encrypted the MMC block 1P4, which is a partition on the SD card. And as a result, encrypted block device is created in the device mapper infrastructure, and it's mounted here in this /MNT encrypted new. So we have used the black key to create this encrypted volume in the device mapper function. Let's take a look using the DM setup table show key command to see what is this encrypted volume here. So as we can see, the kernel crypto API use this new cryptographic transformation, which is indexed there by TK, the tag key, which uses the CBC AES for the storage encryption itself, doesn't mix it up with the key wrapping and black key encryption, which was AES, ECB or CCM, but the storage encryption here can be either ECB or CBC. And the IB generation mode that we see here for this encryption is plain. And for the next field, we have the 48, the size of the black key that we were talking about, how this, what kind of key it is, and how it's been added to the kernel keyring as a logon key that we also mentioned during the presentation slides, and then the key name itself. So this was actually the contents of this encrypted new volume. So now we're going to actually create just a test file on the mounting point of this encrypted volume. And we're going to echo some text in it. Let's say test. And we are going to read it back. Okay, so far so good. Now we are going to unmount this mounting point of this encrypted volume on our flash. Of course, yeah, and for the next step, we are going to remove this encrypted volume from the device mapper. infrastructure. And of course, now this dm setup table show key command doesn't give us any information because we have removed it. But this has already been done during the boot process using the init script where we have actually decrypted and created this encrypted volume. But now for demonstration purposes, I try to remove it, the mounting point, and also remove the encrypted volume from the device mapper infrastructure, and then try to access directly to somewhere, to a mounting point, which is this test directory somewhere. Let's see if this is possible or not. So we created this test, and now we want to mount the volume that we have already, the partition that we have already encrypted on this. And as you can see, this is not possible anymore since the SD card partition is already encrypted using the decrypt in a device mapper infrastructure, and any access out of this infrastructure is not possible. So here we saw that how we have encrypted this storage, and how when it's not actually mounted and created, it's not possible to access it. One other test could be if someone can take this SD card and try to mount it, let's say on a different device, or try to break it. But here we just wanted, for demonstration purposes, to have some simple cases, test cases, let's say. By this, I just wanted to say thank you to all of you that have been listening to the presentation. And here at the end, I have also provided all the references that if someone is interested, they can refer to the references. And now I would be happy to answer the question from the audience.
Okay, so at first, thank you very much for sharing this knowledge and also the deep technical stuff with us. Let's start with the questions. We received a question regarding certificates. The certificates you are used, are these self-signed certificates? And if yes, is then the certificate authority integrated in the embedded device itself?
Yeah. So let me just jump to the slides that we are explaining this concept. So as we can see here, only the root certificate, which is the CA certificate, is a self-signed certificate, because in a public key infrastructure tree, we cannot sign, let's say, the root certificate, the CA certificate. This is a self-signed, and in this project, we have used the OpenSSL, which plays the role of the CA itself by creating the self-signed certificate. But then all the lower levels, let's say the SRK public key, is signed with the CA private key, all of them, and consequently one level, and similarly one level down, the CSF and the image keys, public keys, are signed with this RK private key. But if I understood right the question, yes, the CA is a self-signed certificate, and in a real case scenario, the CA should be really protected in a premises. But at the moment, this is located in my computer, so it's not safe. But in the real case scenario, this can be stored in the hardware security module. But the protection of the CA keys and certificate, the root certificate, is one of the responsibility of the certificate authority. But here we have used the OpenSSL, as we mentioned earlier, as the CA, and also for signing. Yeah.
Okay, so thanks for answering that. Then there is another question. We have seen several steps you showed to us with different signature calculations and different encryption, decryption parts and so on. Can you recommend if we build up a real device based on the i.MX6? What is the absolute necessary things we have to do can guarantee at least the minimum level of security?
Okay, I'm not at the position actually to recommend the solution from the NXP. The reason that I have used this is actually one of the few architectures on the market that you are able to establish the whole chain of trust. If you look at other vendors, those information that the root of trust is established at the bootstrap stage on the hardware are not disclosed publicly. Sorry, but the NXP has done this for this specific i.MX 6 application, but it's of course had its own vulnerabilities, but they have been fixed and is still on the market, and one can still rely on the security mechanism implemented on it. So I would say it's quite okay that somebody can have it in the product, but depending if somebody wants to move to the new generation advanced high assurance boot, that they are actually using the concept of the ARM trusted firmware and ARM trusted execution environment, that's also a different question, because that is different from the i.MX 6 family, and i.MX 7 is also different, and i.MX 8 is actually supporting this. But as I said, I cannot recommend, but based on my experience and the implementation and verification that I did, it's quite a good platform that can be actually used for these purposes. But at the end, depends in the design of the product. Security is one aspect. If security plays a critical role, then all this stuff regarding the security must be considered. But could be an i.MX won't be a good option, let's say, for some specific areas. Could be some different vendors are providing different architecture and they can be used. But then one should see what about the security there. But as I said, if you get a version that the vulnerabilities are fixed at the boot RAM, this device is reliable, and people are producing product and passing certification based on that.
Okay. So thanks so far. We don't receive more questions at the moment. So this shows it could be that your presentation was very complete with content. It was good understandable, or maybe the participants needs some more time to think about to come to some questions. But because the reason that at the moment we don't have questions, I would give you the chance to say some final words to the participants for today.
Yeah, thanks, Sven, and the whole team of the SRG. First of all, I just want to say thank you to the Automotive Security Research Group, and the idea that I really like, that we have a community and we share the knowledge together and we can discuss this stuff. This I really like, and is very unique work from the SRG, and I really appreciate it. And that's why I also wanted to part of this process and try to explain some concept regarding the security, because I see still there are so many problems because of not having a good understanding what is a chain of trust and how the whole system works, and could be people are doing design mistakes by establishing, let's say, for example, a root of trust at the bootloader level and think that they have a complete chain of trust, which is not true, because the boot RAM is missing in that chain. That's why, to make it short, that was my aim, and I'm really happy to part of this community, and hopefully we can come with some new interesting webinars and interesting topic in the future. So, but please feel free, if there is some still questions, you can reach me, and through my LinkedIn profile, so it's all okay, and I can actually try my best to explain if there are some, let's say, questions regarding the chain of trust on an embedded Linux platform, specifically on this platform. Yeah.
Okay, so again, from my side, also thank you to share all the knowledge with us, and we are also, of course, happy to have you in our community. To the audience today, also thank you for participating. I wish you a nice evening, a nice afternoon or morning, wherever you are in the world. I hope you enjoyed the presentation today. I hope also that we provide in the next weeks some other topics you are interested in, and we see us again, or hear us again at least. And that's all from my side. So